Neural networks have revolutionized artificial intelligence, providing breakthrough capabilities in computer vision, natural language processing, and other complex tasks. This introduction will cover the most impactful neural network architectures fueling modern AI. The benefit of knowing the different types of neural networks is for critical evaluation of AI tools for future-proofing careers against tech disruption to aid in public discourse, and because it simply demystifies AI. There are several main types of neural networks, each with their own architecture designed for different applications. This video provides an overview of the most widely used neural networks, including feed-forward neural networks for pattern recognition, convolutional neural networks for image processing, recurrent neural networks for sequential data such as text, transformers for natural language tasks, and generative adversarial networks for data generation. We will discuss the key characteristics and use cases of each neural network type. Also note that while we talk about individual types of neural networks are often used in an ensemble of multiple neural networks simultaneously. Ensembles are good for reducing the variance of predictions and reduce generalization errors that can occur when using a single neural network. The simplest or most basic type of neural network is a feed-forward neural networks, or FFNs. FFNs are characterized by information that flows in one direction only, from the input layer to the output layer. This linear flow of information is advantageous for tasks that require a direct relationship between the input and the output. That is, FFNs excel in situations where each piece of data can be evaluated solely on that piece of data and is not influenced by data from another time or spatial location. Some of the most common uses of FFNs are in applications that require pattern recognition. Some key examples are in personal assistance for predictive typing, in search engines to improve the efficiency and accuracy of search algorithms, in self-driving cars to interpret sensory data for making driving decisions, and for forecasting and estimating outcomes based on historical data, such as financial market prediction. Next is convolutional neural networks, or CNNs. CNNs are designed to process grid-like data, such as images. Unlike feed-forward networks, CNNs are particularly adept at recognizing spatial hierarchies in data, making them highly effective for image recognition, computer vision, and similar tasks. An example of spatial hierarchies in data are geographic information systems, or GIS. GIS data are arranged in a hierarchical layer from global data to continental, to country, to state, to local, to site-specific layer. Each layer provides data with increasing detail and specificity, suitable for various scales of analysis and decision-making. CNNs have revolutionized computer vision, providing incredible performance in image classification, object detection, and facial recognition. Their ability to learn spatial hierarchies of features automatically and adaptively from input data sets them apart from other types of neural network. Next is recurrent neural networks, or RNNs. RNNs are designed to handle sequential data. They have loops within the network that enable information to persist across different steps in a sequence. This structure allows RNNs to remember past information, making them suitable for tasks where temporal dynamics and sequence continuity are necessary. A common use for RNNs is in language translation. RNNs work well at language translation because they can remember previous inputs. For effective language translation, remembering the context and order of each word is crucial for understanding the meaning of a sentence. This ability of RNNs to handle sequences also makes them ideal for various tasks beyond translation, such as text generation, speech recognition, and sentiment analysis. Next are transformer networks. Often, when we think of AI, we are thinking of a transformer neural network. AI applications, such as ChatGTP, are based on transformer architecture. In fact, the T in GPT stands for transformer. Transformer networks represent a paradigm shift in machine learning, particularly in natural language processing. Unlike most other neural networks which process input data in a sequential manner, transformers are able to process input data by dynamically weighing the influence of different parts of the input data. This is a mechanism called attention. The attention mechanics in transformers allows the model to handle long-range dependencies and understand the context in sequences. Additionally, because the attention mechanism processes all parts of the input in parallel, It allows for significantly faster and more efficient computation. Next is generative adversarial networks, or GANs, are used in image and art generation. GANs have gained significant use recently due to their ability to generate data that is indistinguishable from real data. And yes, GANs are at the heart of much of the AI controversy you hear today. GANs consist of two networks, one to create data, the other to evaluate it. The creation network of a GAN is called the generator or generative network. The evaluation network is called the discriminator or discriminative network. The generator and discriminator work against one another in a cycle, continuously generating and rejecting until the generator develops realistic data. There are many additional neural networks with a varying range of purposes, some of the more well-known are Boltzmann machines, which are used to learn features from unlabeled data, such as extracting patterns from images or text. Long short-term memory networks are used in time series prediction, speech recognition, and machine translation. Radial basis function networks are used for pattern recognition for localized data such as text classification and image recognition. Self-organizing maps are used for data visualization, customer segmentation, and feature detection. Capsule networks, or CAPSnets, are used for object detection, image segmentation, and other tasks where spatial hierarchies are necessary. Spiking neural networks are used in robotics or when real-time decision-making is necessary. Echo state networks are used in time series forecasting and dynamic system modeling. Again, these are just a few of the ever-expanding toolbox of neural networks. The choice of which neural network to use depends on the specific characteristics and requirements of the purpose at hand. Summarizing the primary takeaways from this video. 1. There are many different types of neural networks, each with unique characteristics and purpose. 2. Transformer neural networks represent a paradigm shift in artificial intelligence with applications such as ChatGTP. Transformers are unique in that they are able to process input data by dynamically weighing the influence of different parts of the input data. 3. Convolutional neural networks, or CNNs, are designed to process grid-like data, such as images. CNNs are particularly adept at recognizing spatial hierarchies in data, making them highly effective for image recognition, computer vision, and similar tasks. 4. Generative adversarial networks, or GANs, are used in image and art generation. GANs have gained significant use recently due to their ability to generate data that is indistinguishable from real data. I hope you found the video to be informative. Thanks for watching.